Hi, it's Saikur Rahman. So I'm going to start my first video presentation of assignment number 1 of artificial intelligence course. The assignment is about reinforcement learning basics. So in this assignment, we're going to use an OpenAI library, Gymnasium, and in Gymnasium we're going to find some classical control environments mechanism, and here we'll going to start with Cartpole, mountain car, and other control environments. So this is the mountain car that can move back and forth, and its target is to go to the top of the hill where the yellow flag is kept. And the second one is the cart pole, and here this is cart is moving left and right, and the pole is trying to balance itself. That is, it wants to stay upright. So these are the two control environments we are going to deal with today. So at first we have to know about the create the environments. So we need to find or we need to show the characteristics of the environment in detail. So first I want to discuss about the environment of cart pole, and here there are two action space, that is the cart can move in the left position or right position. So, and these actions are specified by 0 and 1. And the thing that should be observed here, that is the 4 observations. So it has the shape of 4 values. This is the card position, that is along the x-axis. So the minimum value and maximum value is within 0.4.8. And there's the car has some velocity, and there is the angle, the pole angle, where the pole angle can have any value within this range, that is minus 24 degree to plus 24 degree. And it has some rewards. If the pole is kept upright, it has some reward +1, and it is going on. And if the threshold becomes 471 for version 1 type, so we can say that the algorithm is properly um, installed in the machine. And there are some termination topologies, that is, if the pole angle becomes greater than plus minus 12 degree, then the episode will end, or the card position is greater than 2.4 or minus 2.4, it will terminate. And the episode length is greater than 500 for version 1, whereas it is 200 for version 0. Then you want to show the environment of mountain car. It has only three state, that is action space, that is, it can accelerate to the left, it can't accelerate, and it can accelerate to the right. It has so the numerical values are 0, 1, 2. Observation space, that is the position of the car and the velocity of this car, and it has a value that is a minus 1.2 to 0.6. This is for position, and for velocity this is from minus 0.07 to plus 0.07. And the reward is the target is to reach at the top of the hill. So if it can't, then it will be penalized with -1. And the episode can end if it has some termination policies. The termination policy is if the position of this car is greater than or equal 0.5, then it will be terminated. And as it is version 1, the length episode is 200 for truncation. And these functions can be imported by this argument, import gymnasium as gym, and gym.make mountain car version 0, and for cartpole it is cartpole version 1. Then we can start seeing the codes. So at first we have to make the environments for the two different cartpole and mountain car control environments. And then we're resetting the environments, and we're printing how many actions in mountain car environment and cartpole. And it is seen that in mountain car there are 3 actions, that is accelerate to the left, don't accelerate, and accelerate to the right. And for cartpole there is 2 actions, that is moving right or moving left. And then using step function, we are just advancing in the environment by a one-time step. So at first, from this environment action sample space, randomly the action was taken, and the information, that is observation, reward, termination, truncation, and other information can be printed here. That is, if we run take a random action from mountain car environment, we can see that the input action is 2. That is, the mountain car has some acceleration in the right direction, and there's some observation. That is, the first one is the position of this car, and second one is the velocity, so which is a two shape. And as the position is -4, so termination is false, because the condition was if the position is greater than 0.5, then it will terminate. And as the episode number is not beyond 200, so it is also not truncated, and the reward is -1. So these are the output values of we can find any random actions of mountain car environment. And instead of performing some random actions, if we take some specific actions for mountain car environment, then we are taking the first exercise is told that to take at first 5 actions in the right movement, and then 5 actions in the left movement. Then the action sequence can be defined as an array of 5 ones and 5 zeros. And initially, from initialization, it is taken terminated has been false, is no termination of actions. And we can put it in a for loop for taking the actions in one by one, and observe the outputs. That is what is the observations, reward, termination, truncation, informations. So there are in total 10 actions, and for each observation, if we can see the first observation, the position is 0.23, and but the pole angle is beyond 0.42. That's why this has been terminated. And again, the pole angle is beyond 0.42 in each cases. That's why it is terminated in all the cases, in all the 5 right movement, and for all left 5 left movement, the pole angle is greater than the 0.42 degree 42 radian. That's why it has been terminated in each cases. And if we want to do the same thing for mountain car, then at first we have to reset the environments, and we can observe the initial positions of 2 environments, and we can print the limits, that is upper bound and lower bound of the observations. That is, for Cartpole, the minimum value was -4.8 to maximum value was 4.8. And for mountain car, the minimum and maximum was defined as this is the car position, and this is the velocity of this. So that's all about experiment 1, that is to have some specific actions and resetting and observing the initial outputs of the 2 environments. The second exercise was to deal with the Acrobot environment and find how many actions are there, and resetting the environment, initial observations, and the maximum minimum limits. And that we just did for the other 2 environments. So if we go to the background of Acrobot environment, then we can see that there are 3 action spaces. That is, there are 2 joints, so it can have some torque in left direction, right direction, or can be stable. So the number is 0 if a -1 torque is applied at the actuated joint, and it can have some value of 1 if there is no torque, and if the number is 2 if there is a positive or +1 torque in the actuated joint. And the observations are there are at least in total 6 observations. The main thing is dependent on θ1 and θ2, where the θ1 is the angle of the first joint and θ2 is the relative angle of the 2 joints. And the minimum and maximum value of the theta is -1 to +1. And the reward is if it cannot find the ultimate goal, then it has to be penalized in -1, and if the threshold is set to -100, and if the target is achieved, it is rewarded with some value 0. So for similarly, we're just loading the Acrobot version 1 environment and we're printing the number of actions, and in total there are 3 actions. And if we want to see the initial observation, then we see that is initially the cosine theta 1 is 0.1, that is almost 0, so it is value is almost 1, and similarly theta 2 is almost 1. And maximum and minimum limit that I showed in the Acrobot environment is -1 to 1, and the random action was taken as +1. That means it has no clock is applied and the reward is -1. So the final exercise is about to find the cumulative reward and to maximize it, and to train the machine or to train the model with some algorithm. And here we'll just use the PPO algorithm, which is known as a proximal policy optimization model. So for that, at first we're just installing a stable base 3 library here, and also we're going to apply it on our Cartpole environment. That's why we are also um, loading the Gymnasium library here, and all the other necessary functions that are needed here. And as we are simultaneously using gym and stable baseline databases, so we can get some errors, and so this is the way how to ignore the errors. And using pandas, numpy pandas in uh, and matplotlib.pyplot as for the plotting functions. So first, the Cartpool version 1 environment is created and the login directory has been assigned. And there is creating some environment that has to be monitored. This is the function is called name Cartpool environment monitor, and it has some arguments. So this is the multi-layered perceptron policy that has to be trained in the model. It is called agent for Cartpole PPO algorithm we are going to use. So we're just writing a callback function to record the reward in the whole process, and we're just trying to see the we're going to call the reward function after some certain episode. And for example, there is 200 episodes, and after each episode we are just going to find the mean values of the reward. So if we run the program for 20,000 time steps, and we can see the time step values and mean reward of the latest 200 episode, and it is getting bigger and bigger. So the algorithm is successfully trained to the model. And finally, it has some values we can get, that is finally when the time steps, final time steps come, the mean reward is almost 87.86. Now this is the time to plot the reward functions in graphical format. That's why we're just importing the reward values in an array, and we are just plotting it in some figure that is in a rectangular form of 10 to 5 height and width, and we're just taking the reward data as in x-axis plot and in y-axis plot in reward per episode. Then we are seeing that in 30,000 episode it has reached some values at 500, and as we said that is 475 is the threshold, so we can say that the model PPO algorithm has been successfully trained the model, and the Cartpole environment is able to become upright, so it has got some good reward. And we can also evaluate the policies of 100 episode, and we can observe the mean using that function evaluate policy. And we can find that the 100 after 100 episode the mean reward is 500, that is the threshold. So finally, if we want to see the what the output effects in the video format, then we can use that functions, the video recorder, and after some video rendering we can see that the cut pole is now balanced and the pole is in upright position. So after applying the PPO algorithm to the model, the environment has been able to stay in upright. So, and we can also find it is verified after seeing that the reward is 500 and that is greater than the threshold value. So this was all about assignment 1. Thank you.